நீங்க வீடியோ வேணா இப்போ ஆஃப் பண்ணிடுங்க. நம்ம லைவ் வந்துட்டு மக்கள் வந்து ஜாயின் பண்ணும்போது நம்ம அப்புறமா ஆன் பண்ணிக்கலாம். வீடியோ மட்டும் இப்போதைக்கு. ஓகே ஃபைன்.
இப்போ என்னுடைய வாய்ஸ் கேக்குதா சார்? கரெக்டா இருக்கா?
ஓகே. லைட்டா எக்கோ இருக்கிற மாதிரி இருக்கு. ஓகே, நோ இஷ்யூஸ். நீங்க ஓகே ஃபைன். பட் அந்த வீடியோ கொஞ்சம் கிளாரிட்டி போயிட்டு வருது. ஓகே, நல்ல கிளியரா இருக்கு. ஓகே
ஓகே
ஓகே. ஸோ the people are joining.
we will wait for some 5 minutes.
Yes. Sure. Hi, participants. We are a bit early. I will wait for another 3 minutes. So let others join. I request whether we are audible. Just you can type yes in the chat box if you are audible. It's okay.
Sir, you can start the presentation from your side, right?
Yes. Yeah.
Okay, fine.
Yes, you can give me caution accordingly.
Okay, fine.
Okay. Let's start. Good evening. A warm welcome to you all. On behalf of Jaya Group of Institutions, we welcome you all to this webinar on artificial intelligence vision technology, making machines to see. Today we are pleased to welcome Ms. Rekha Jayaprakash, the renowned and proud alumni of our college. Now she is the scientist, imaging and vision technology, Fraunhofer Heinrich Hertz Institute, Berlin, Germany. A very young scientist, as per my observation as a student during her undergraduate. She is a hard worker, always hunger for knowledge, very committed and sincere on her work. We extend a warm welcome to you, Rekha. And today, Mr. Rekha will be sharing with us her expertise in the area of vision technology. It's my honor and privilege to introduce Ms. Rekha Jayaprakash. She has completed her Bachelor in Computer Science Engineering from Jaya Engineering College, Anna University. She's a university rank holder and a Master in Technology in Mechatronics from CSIR's academy body named SCSIR University, New Delhi. She started her career as a scientist in Central Mechanical Research Institute in Durgapur, West Bengal, in the field of surface robotics. Later in 2012, she moved to Germany to work on a European Union project in the field of 3D computer vision at the University of Hamburg. Thereafter, she moved on to the Technical University of Hamburg as a scientific staff to work on 3D vision system development in laser welding technology for the ship industry. Later, she joined Fraunhofer, Europe's biggest applied research organization, to work on additive manufacturing quality assurance system for 3D metal printing machines, immersive technology-based applications using virtual reality and augmented reality devices, and contactless application development for industrial robotics, and many other vision applications. With this brief introduction, I request Mr. Rekha Prakash to present. And before getting into the session, kindly note the points as usual we do. So at the end of the presentation, uh, everyone should submit a feedback form. Okay, so otherwise the certificate will not be generated. And if you have any queries, please post in the chat box so that we will address all your questions at the end. So without wasting our time, we will move on to the session. Over to Rekha.
Thank you so much for the warm welcome, sir. Good evening, good afternoon, good morning to everybody who is present over here. I don't know where from you are log on into this webinar. So I would like to switch off my video so that you can have a bandwidth. We can switch over to the talk. Sir, can you start the presentation?
Just a minute. Yes.
So once again, a very warm welcome to everybody. So I think I'm audible to everyone. We had some bit of technical issues before we were sorting out. Am I audible to everyone? Okay, fine. Okay, so today I'm going to give a presentation about vision technology, how to make missions to see, which sounds very exciting. And the talk is going to be very general insight into the field of AI vision. So it's not very technical. My aim is to engage you all and induce your interest and curious about this particular interesting area of AI vision technologies. So I'm sure that in 1 hour we cannot try to solve some mathematics or something. I just want to give a brief introduction into several other sectors, industries, and domains of engineering, medical, and whatnot of this AI vision technology, so that you yourself can explore this area and you can take upon your career, you can take upon your research direction, you can take upon your teaching profession or anything in this area. You can also do a small project or so on. So I really want to captivate you in this topic. So feel free to ask any questions. I would be happy to answer your questions at the end of this session. So let's get started. I've just given an overview. This is not going to be a conventional type of talk. It's just going to be a relaxed one. It's of course weekend. I want you all to leave with some food for your brain so that you can think on your own. I'm not going to spoon feed you everything, to be precise. So next slide. Before starting this video, I want everybody to uh, observe this video, and whatever robots and missions that are shown in this video have certain common features. So we will talk about that later on once the video is completed. So can you start the video?
Yes.
Despite taking people's jobs, robots have been proven to be essential in improving efficiency, productivity, and most importantly, worker safety. In this video, we are going to look at the most advanced humanoid, industrial, and service robots that are changing the future with the help of artificial intelligence. Meet Digit. Manufactured by Agility Robotics, Digit is envisioned to help take care of people in their homes, assist with disaster response, and deliver packages to front doors. With its nimble limbs and a torso packed with sensors, Digit can navigate complex environments and carry out tasks such as package delivery. Digit is a direct descendant of Cassie, Agility's first robot. In May 2019, Ford Motor Company and Agility announced a partnership to develop a last-mile logistics solution that combines Ford's autonomous vehicle technology and Agility's Digit. This is Pepper. Manufactured by SoftBank Robotics, Pepper is the world's first social humanoid robot that is able to recognize faces and basic human emotions. Pepper has been adopted by over 2,000 companies around the world. Perfect in retail and finance industries, Pepper has numerous functionalities, including increasing store traffic by attracting the attention of shoppers, creating memorable in-store experiences, stimulating purchase and retain customers. Pepper can also gather comprehensive data to enrich the customer base and generate shopper insights. This is Atlas, the world's most dynamic humanoid robot built by Boston Dynamics, a company that was previously owned by Google and now by SoftBank. Thanks to its state-of-the-art hardware and algorithm that allows it to quickly understand instructions. With its 28 hydraulic joints, 4.9 feet of height, and 176 pounds weight, the robot can perform both impressive and terrifying acts, including navigating uneven terrain, jumping around a parkour course, and doing somersaults. All these activities demonstrate human-level agility, so the robot can be perfect for search and rescue operations and performing human tasks in environments where humans could not survive. Introducing Spot, a robot dog designed for industrial uses, such as carrying goods through a warehouse and inspecting a remote site with an unfavorable environment for human operators. robot can run at 5.2 feet per second, has 360-degree cameras, and can operate in temperatures ranging from 4 to 113 degrees Fahrenheit. With its API and flexible payload interface, the robot can be easily customized for desired tasks. Spot is also manufactured by Boston Dynamics and is now being leased to eligible companies. Meet HRP-5P, an advanced humanoid robot designed to operate autonomously and carry out heavy labor in hazardous conditions. This robot was created by AIST, Japan's National Institute of Advanced Industrial Science and Technology, as a response to the country's labor shortage due to its aging population and declining birth rate. It is equipped with environmental sensors and object recognition, full-body motion planning and control, and task description and execution management. HRP-5P is based on more than 20 years of humanoid research at AIST. In those 20 years, the Institute has created 4 other robots, which are the predecessor of HRP-5P. Introducing Serena 4, the 4th generation of Serena humanoid robot series developed by the University of Tehran in Iran. With a height of 5.6 feet and a weight of 154 pounds, this robot is able to walk at a speed of 0.43 miles per hour. Serena 4 has improved interaction with the environment. It can track objects more accurately compared to its predecessors. Its new hands give it better dexterity. With these enhancements, the robot can manipulate a wide variety of objects, including delicate ones, as well as operating power tools. Introducing Aquanaut, an advanced unmanned underwater transformer that can transform itself from a nimble long-distance submarine into a half-humanoid robot capable of carrying out complex underwater manipulation tasks. Designed by Houston Mechatronics Inc., Aquanaut can inspect subsea oil and gas infrastructure, operate valves, and use tools. Operating completely untethered and without support ships, Aquanaut can travel more than 124 miles in submarine mode, has a max speed of 7 knots, and a maximum operational depth of 984 feet. This is a Stunttronic robot, an animatronic stunt double designed to entertain the crowds at Disney parks. It combines advanced robotic technology with the exploration of untethered dynamic movement to precisely perform aerial flips, twists, and poses. With its onboard sophisticated sensors, it can make its own real-time decisions, all while flying 60 feet in the air. It knows when to tuck its knees to perform a somersault, when to pull its arms to twist, and even when to slow down its spin to make sure it makes a perfect landing. This robot is called Handle, another robot from Boston Dynamics. With its deep learning vision software, this robot can autonomously identify and locate boxes, unload trucks, palletize it, and depalletize it. It can pick up to 360 boxes an hour. Its swinging tail helps it balance movements and counterbalance the weight of a heavy box. The two wheels are used for fast and efficient flat surface movement, while the legs are used to take it anywhere. What do you think of these robots? What areas do you think we need more robots or no robots at all? Please let us know in the comments section below. And please don't forget to like and share this video with your friends. Thank you for watching.
Hello. Yeah, we are back. Can you able to hear me now?
Yes, Rekha. Go ahead.
Yeah, okay, I'll continue. So we saw a video which consists of most of the available existing prominent humanoid robots, industrial robots, robots which are shaped like other forms like animals and different terrain robots, underwater robots, and so on. So we could able to see one of the most common features, the common technology that has been used in all of these complicated, sophisticated missions. So which is vision system. So as you can see, whether the robot is used in logistics, retail, delivery, or underwater, or even if it is in a different environment to help, whether it's a high temperature, low temperature, different sort of terrains, they use certain form of sensing to see the physical world, and then they try to understand it and try to take a decision based upon what they see. In the first example, you saw a delivery robot which was following its path and then trying to avoid some obstacle on the way, which is being observed from the sensors, and then it's taking a different path. So that is a decision taking. So this is one of the examples of where the vision system comes into play. This is the core of the vision system. So any decision to be taken based on the dynamics of the environment, the mission has to see and act accordingly. So the seeing, processing, and acting accordingly is what comprises of the vision system. It's all comprising of the vision technology. So the sensor can be of cameras, which can be of anything else that we will talk about later. And I really wanted to explain through this video that what is the core of the vision system that we are dealing with here. Next slide. As you can see, the picture is like a little bit not so full. The vision, what is vision, AI vision system? So we are dealing with identifying, recognizing, classifying, tracking, sorting any sort of information that is available. Is the audio good now?
Now it's okay.
Okay, fine. So any sort of physical entities that we see in the world has to be understood by any machines. That's what comprises of this visual AI. Next slide, sir. So what we are trying to do is we are trying to mimic the human visual system. For example, in the image given, there's a bowl of different sorts of fruits. In a fraction of a second, human being can see the picture and say, yes, there is a bowl of different sort of fruits. How many fruits are there? What is the color of the fruit? And how it is placed? What is the shape of the bowl? And everything you can say in a fraction of a second. We want that kind of accuracy, precision, and processing speed in missions. So that's where the computer vision system, the AI vision system comes into play. So we want missions to process whatever input is given through image and video and try to get the understanding of the image content. So the image content can be of anything which is existing in the physical world. So I would like to show you a video of how this particular vision system works, because we need to dissect each and every individual parts of how this particular vision system works. I showed you complex missions that exist now. So it looks cool and very captivating to see such robots in action, but how difficult it is to make such kind of visual sensing that exists in human into the mission is very complex. So before moving on to the particular video which explains about how computer vision really works, I would like to really give you a difference between what is image processing and computer vision. Because next slide. Because many people get confused with okay, this is all about image processing. No, image processing is also a part, but we have to understand the basics. Image processing always involves image as an input, and it is processed through some algorithms, for example filters, and then it throws out image as output. In computer vision, we also have streams of image or image through any kind of sensors. We process it through algorithms, and then we get inference and insight, like what is the image content. For example, that we saw the bowl of fruits. Let's move on to the video, which explains beautifully about how this particular black box called computer vision system works. Sir, can you play the video?
Yes.
Human vision is amazingly beautiful and complex. It all started billions of years ago, where small organisms developed a mutation that made them sensitive to light. Fast forward to today, and there's an abundance of life on the planet which all have very similar visual systems. They include eyes for capturing light, receptors in the brain for accessing it, and a visual cortex for processing it. Genetically engineered and balanced pieces of a system which help us do things as simple as appreciating a sunrise. But this is really just the beginning. In the past 30 years, we've made even more strides to extending this amazing visual ability not just to ourselves, but to machines as well. The first type of photographic camera was invented around 1816, where a small box held a piece of paper coated with silver chloride. When the shutter was open, the silver chloride would darken where it was exposed to light. Now, 200 years later, we have much more advanced versions of the system that can capture photos right into digital form. So we've been able to closely mimic how the human eye can capture light and color. But it's turning out that that was the easy part. Understanding what's in the photo is much more difficult. Consider this picture. My human brain can look at it and immediately know that it's a flower. Our brains are cheating since we've got a couple million years worth of evolutionary context to help immediately understand what this is. But a computer doesn't have that same advantage. To an algorithm, the image looks like this. Just a massive array of integer values, which represent intensities across the color spectrum. There's no context here, just a massive pile of data. It turns out that the context is the crux of getting algorithms to understand image content in the same way that the human brain does. And to make this work, we use an algorithm very similar to how the human brain operates, using machine learning. Machine learning allows us to effectively train the context for a dataset, so that an algorithm can understand what all those numbers in a specific organization actually represent. And what if we have images that are difficult for a human to classify? Can machine learning achieve better accuracy? For example, let's take a look at these images of sheepdogs and mops, where it's pretty hard even for us to differentiate between the two. With the machine learning model, we can take a bunch of images of sheepdogs and mops, and as long as we feed it enough data, it will eventually be able to properly tell the difference between the two. Computer vision is taking on increasingly complex challenges and is seeing accuracy that rivals humans performing the same image recognition task. But like humans, these models aren't perfect. They do sometimes make mistakes. The specific type of neural network that accomplishes this is called a convolutional neural network, or CNN. CNNs work by breaking an image down into smaller groups of pixels called a filter. Each filter is a matrix of pixels, and the network does a series of calculations on these pixels, comparing them against pixels in the specific patterns the network is looking for. In the first layer of a CNN, it is able to detect high-level patterns like rough edges and curves. As the network performs more convolutions, it can begin to identify specific objects like faces and animals. How does a CNN know what to look for, and if its prediction is accurate? This is done through a large amount of labeled training data. When the CNN starts, all of the filter values are randomized. As a result, its initial predictions make little sense. Each time the CNN makes a prediction against labeled data, it uses an error function to compare how close its prediction was to the image's actual label. Based on this error or loss function, the CNN updates its filter values and starts the process again. Ideally, each iteration performs with slightly more accuracy. What if instead of analyzing a single image, we want to analyze a video using machine learning? At its core, a video is just a series of image frames. To analyze a video, we can build on our CNN for image analysis. In still images, we can use CNNs to identify features. But when we move to video, things get more difficult, since the items we're identifying might change over time. Or, more likely, there's context between the video frames that's highly important to labeling. For example, if there's a picture of a half-full cardboard box, we might want to label it packing a box or unpacking a box, depending on the frames before and after it. This is where CNNs come up lacking. They can only take into account spatial features, the visual data in an image, but can't handle temporal or time features, how a frame is related to the one before it. To address this issue, we have to take the output of our CNN and feed it into another model which can handle the temporal nature of our videos. This type of model is called a recurrent neural network, or RNN. While a CNN treats groups of pixels independently, an RNN can retain information about what it's already processed and use that in its decision-making. RNNs can handle many types of input and output data. In this example of classifying videos, we train the RNN by passing it a sequence of frame descriptions, empty box, open box, closing box, and finally a label, packing. As the RNN processes each sequence, it uses a loss or error function to compare its predicted output with the correct label. Then it adjusts the weights and processes the sequence again until it achieves a higher accuracy. The challenge with these approaches to image and video models, however, is that the amount of data we need to truly mimic human vision is incredibly large. If we train our model to recognize this picture of a duck, as long as we're given this one picture with this lighting, color, angle, and shape, we can see that it's a duck. But if you change any of that, or even just rotate the duck, the algorithm might not understand what it is anymore. Now, this is the big picture problem. To get an algorithm to truly understand and recognize image content the way the human brain does, you need to feed it incredibly large amounts of data of millions of objects across thousands of angles, all annotated and properly defined. The problem is so big that if you're a small startup or a company lean on funding, there's just no resources available for you to do that. This is why technologies like Google Cloud Vision and Video can help. Google digests and filters millions of images and videos to train these APIs. We've trained a network to extract all kinds of data from images and video so that your application doesn't have to. With just one REST API request, we're able to access a powerful pre-trained model that gives us all sorts of metadata. Here's how easy it is to call the Cloud Vision API with curl. I'll send this image to the API, and here's the response we get back. Billions of years since the evolution of our sense of sight, we found that computers are on their way to matching human vision, and it's all available as an API. If you'd like to know more about the Cloud Vision and Video APIs, check out their product pages at the links here to see how you can easily add machine learning to your application. Thanks for watching.
Next slide, please. So the video summarizes how you can recognize image, a static image, and it also shows how you will recognize the sequence of events in a video. So those are like two different problems that we frequently come across in computer vision. So the complex problem gets even more complex when it is implemented in a mission which is also moving. So we have a lot of cameras installed in a particular mission which constantly captures the environment which is in. For example, take a spot robot, which is like four-legged robot, which is having 3D sensors and two cameras, which is constantly sensing the 3D world, and it is constantly looking for some information. For example, if something comes across in front of the robot, it has to immediately stop or take an action to go back, or whatever it is doing, it has to stop. So it has to sense continuously in order to avoid this collision. We saw how computer processing sequence of images is getting complex, and we have to go for more complex machine learning models. Here she explained about two conventional models, which is CNN and RNN. CNN is most widely used model, a convolutional neural network, which takes decision based upon what input is given. So RNN is something which we need for dynamic environments, because we need to know what existed previously, what is happening now, and what is going to happen next. So it's like n t minus 1 frame, t frame, and t plus 1 frame. So we need to know all these three information in order to take a action or understand what is happening in the physical world. So now we talked about how this black box of computer vision works. And let's go back to even more detail. Like the first step in constructing any vision system is to have a proper sensors. So it's a particular big topic where what kind of sensors are used, how many sensors to use, and where the sensors needs to be placed. These are all, it depends on what kind of mission that you're building, what kind of robot that you're building. So it depends entirely also based on application. So what is the end purpose of the mission? I'm going to generally give a description about the sensors that we can use. Let's keep it simple. The RGB camera that we have normally have in laptops or like webcams. So the construction methodology can be single camera based. Single camera based applications are like numerous. There are so many vast applications. One such thing is you can use, for example, you might have went to this immigration check in airports. They will try to take your photo using one single monochrome camera. So using this camera, they will identify your face, and then they will run this picture of your face in their database of face images to identify that it is you, person named X. And then it recognizes, okay, your details are right, and so on. So this is a simple application which we have already seen in airports, also in some of the banking security systems. So the next type of construction is stereo vision based system. Stereo vision always consists of two identical cameras, two identical RGB cameras, monochrome cameras, or any industrial cameras that you can use, which always placed at a distance, known distance. So for example, we have human eyes, which are like two sensors, identical sensors, which are placed approximately 8 centimeters apart. So it is one of the best examples of stereo vision based system. So you can construct stereo vision for doing 3D based analysis. So we need stereo vision in order to perceive 3D. 3D is like depth. We need depth information in order to say which is in front or which is behind, which is far away relative to some other object. So it is the more prominent way. Am I audible? I
Yes,
see
Rekha.
some of them. Okay, I'll
Yes,
continue.
it's fine.
Okay, thank you. And the most important feature of stereo vision is we could able to perceive depth. The depth information is needed for many kind of application to sense which object is far away or nearby. So the next type of construction is multi-camera based system. So multi-camera based system always have identical sensors. For example, again, industrial cameras, RGB cameras, and so on, which will be constructed linearly or in circularly or in a square based next to each other. One such system, one such example that I can give you is, I'm sure many of you have watched Onion movie, where director Shankar have used 120 cameras, movie making cameras, high definition cameras in a rig. It's like a linear rig where you can see one frame in a 3D way. So you can rotate and completely see the frame in 360-degree. So that's one of the basic usage of that. And next we have multi-sensor based. Multi-sensor based systems are like different types of sensors are used, which will have different characteristics. For example, we have IR, infrared based cameras, LIDAR, sonar, radar, and we can have thermal image, thermal cameras, OCRs, and so on, and multispectral images and channel based imaging. There are so many sensors which are available. So you can construct a particular setup using different kinds of sensors based upon your application. So you can see in the image, a sports player is standing in front of a rig, which consists of 3D sensors, Kinect, constructed in a parallel manner, placed in an equal distance from one another. I can see 3 sensors there. Each of the sensors are 3D. And on the right side, you can see an image where it gives the 3D constructed model of the sports person. This is only one perspective view. If you have the same sort of rig placed equidistance in a circular manner, you can get 360-degree of 3D model of that particular sports person. So where it is used, again, you can create 3D content from the real person, which can be used in many of the VR, AR immersive technologies. So you can use your own 3D generated model in different applications for gaming, for remote video conferencing, like teleporting yourself to the other place. There are a number of applications which I will talk about later in the presentation. Next slide. So now we saw what is vision system consists of, how it works, and how we can construct with the help of cameras. Now I would like to show you some of the use cases and experiments that I have personally worked on. So in the first video, I showed robots, which are like doing some complex tasks like picking, placing, avoiding obstacles, jumping. And for example, if you might have seen, one robot was trying to hold a water bottle. So, and also trying to drill in the wall. So all these they are doing based on what has been given to them, instruction, what they are seeing. And for example, if the robot or the vision system that you're developing has to identify humans, recognize a human, what will be the steps, what we need to do? So that's what I'm going to talk about in the next several slides. So we need to see human body consists of several parts, and we have face, head, hands, torso, legs. So these are the most prominent feature part that we have is face. Face has very symmetrical feature for each and every person. Your eyes are placed in certain distance. Your eyebrows are placed in certain manner and certain distance, orientation, and your nose, nostrils are like unique to you, and you have like certain distance between two of your nostrils and mouth and everything, the shape. So everything is symmetrical on your face. So it gives you a proper prominent feature in order to recognize you as a person. So how a robot can communicate with a human being? We all have seen a movie, Robot 2.0, and then so seamlessly Rajnikant talks with all of the humans and objects, non-living things exist in his environment. It's not so easy to develop such robots. So I'm trying to restrict it to one human being. If there's a one-on-one communication between a robot and a human, the robot has to see the human face. It has to recognize, yes, it is Dr. Vasigaran, or it is like Aishwarya Rai, or it is someone else, XYZ, naming person. And it has to see, it has to communicate based on how the human is communicating. So it has to recognize facial expression. It has to recognize where the face is. It has to recognize where the hands are. It has to recognize how the torso is moving. All these are important information which needs to be identified, recognized, and combined together in order to give a meaningful conversation. Say, for example, in this slide, you are seeing a stereo camera based 3D reconstruction of the face. So on the left, you can see my face, which is captured by two similar identical cameras that I already talked about in stereo vision. We use those systems to reconstruct my face to the 3D model, which you're seeing in the middle. And then from this 3D model, if you have the 3D model exactly reconstructed from your original face, you can use this 3D model imposed on so many avatars. The right image that you see, the bald man, is an avatar. I randomly picked one avatar. This avatar you can generate using any of the computer graphics softwares like Blender, Unity, and all. Many people use it for gaming and 3D content creation for VR technologies. And we don't have to create it right from, like animating and, creating from scratch. We can really reconstruct from real world. You can really create your own self, your own face into an avatar. This avatar, you can use a dragon face or like a puppy or a parrot, anything. So it's one of the examples of how vision system comes into play. If you have two cameras, you can reconstruct 3D of any object. So here we are seeing the example of my face. So all these meshes that you see are very, very important, because when I move my face, my eyebrows up, how my eyes are moving, in which direction, how my lips are moving, and whether my lower mouth is open or not. All these are very, very important, because as I said before, the robot has to identify what your state of mood is. For example, you're sad, happy. If you're happy, maybe your eyebrows are up and your mouth is open and you're like in a complete state. So the robot has to identify this complete expression. So this is one of the example. So where this can be used is, you can think of a medical help robot helping an elderly person who is not able to move properly. He or she may be immobile, or people with limited mobility, people who are like physically challenged. Those robots can really identify their mood and they can take actions. For example, if somebody cannot move their hands, they can only give facial expression. But you need 24/7 monitoring of this particular patient. How we can develop such robots? This simple thing can help them. So the best example would be like we all know Stephen Hawking. He cannot move any of his body parts. He has very limited motion of his facial muscles, through which he has to communicate using a computer system. So likewise, you can use. And another example is we can use this. Another example is we have a multi-sensor based construction here. First, I showed you stereo based. This is multi-sensor based. There's a person standing in front of so many number of cameras which consist of high definition. We have Kinect, we have Carmine. Those are all like 3D sensors. Carmine and Kinect works on the same principle. It emits structured light, and then you get the 3D information from RGB and the structured light configuration. Carmine have short range of working with high resolution. So this is one of the projects that I worked on, where I constructed different cameras with known distances, wherein a full human body can be tracked. As you can see, the person is signing in front of the camera. He is deaf person. He cannot talk. He will communicate only through his hand movements and facial expression and body movements. So now my camera system has to recognize each and every part of it. So it has to see his face separately, hands separately, torso separately. So the Kinect will track the torso and also as well as the legs. The legs are like most less prominent, but hands and face, the head orientations are very, very important. We have to recognize that in 3D in order to get the three-dimensional notations. So in mathematical form. Next slide, sir. Yes. So as I said, we need a different segmentation of head, your hands and stuff. Actually, this was a video. Unfortunately, I couldn't able to play because of some technical problem. But as you can see, the top video gives you movement as motion estimation vectors. You all might have studied probably in digital signal processing or somewhere about some velocity vectors, motion estimation vectors. So that shows the vectors which have moved from the previous frame to the current frame. How much it has moved is represented by the color. The cooler color represents less movement. The hotter colors like red and purple includes the faster movements. So we need different type of segmentation of the human body, and then combine segment. You do the segmentation, and then you identify what each parts are doing, and then you try to combine. Okay, the face is in this orientation, the hands are resting, and the mouthing movement is this way. So you can combine all this information to say the person is not talking or she is sad or something. So these are the this is where a lot of mathematics are used. You need to have understanding of a lot of mathematical background, which I will tell you what you need. Next slide, sir. So as I said, this is also one of the examples of face tracking. So here the scenario is very simple. As you can see, the background is plain. So there is not much objects or lighting difference or anything is not there. So even then it is difficult because the person is moving very fast. So you have to recognize each and every frame, what she is doing, where the hands are moving, what is the orientation, shape relative to the body. Next slide, sir. And okay, we talked about the bigger pictures. Now hands consist of fingers. We need to recognize even the fingers. For example, if I show you 1, 2, 3, so 2 fingers are open, 3 fingers are open. So these things has to be also recognized. So we have different kinds of sensor, which is a small one but very accurate. It's called leap motion sensor. These sensor have IR emitting rays and have a very narrow field of view. So you can move your hands in front of it, and it will give you all the 3D joint position of your fingers. Each and every finger have like 4 joint positions, so it can give you. So based on where your joint positions for each finger, you can recognize some of the actions like pinching, swipe, like pinching, or like bending of a particular finger, or like closing of the fingers and so on. So all these information has to be combined in order to get full meaning. Next slide, sir. Okay, we saw one particular use case scenario which dissects the complete human being recognition. So the next one that I'm going to talk about is human robot interaction. So this is also a computer vision, AI vision technology, where I'm going to talk about one use case, industrial inspection and teaching robots in a different way, not like conventional way. Next slide. So the industrial inspection, as you can see on the left side, we have the real system where the KUKA robot is holding a a car part, which has to be inspected for welding defects. So how we can do the defect inspection, whether the welding has been done correctly, whether the part is joined properly or not, how all these things can be inspected without even touching anything. So this is one example of human machine interaction, which involves, on the right side, you can see the experimental setup that I worked on, where the red markings shows a lot of different cameras which are involved in this particular vision system technology. So the car part is holded by a robot, and the mission operator will be standing next to the part, and he can, the whole interaction, the interactive design interface is projected onto the part itself. So the user, the inspector, can see the part. If the welding is not correct based on the projection, he can just touch the part where it is defect, and it will automatically transfer to the system as a report whether this part is good or how many welding defects are there. So these are like very high level manufacturing production line inspection for quality control systems, which we partnered with Volkswagen. And as you can see, we have a projection system. There is an industrial camera which recognizes the complete part in computer vision. And then there is a tracking part of the inspector, how the inspector hands are moving on the part area, so that it can recognize, okay, he is moving to the upper left, so there's a welding section 1, 2, 3, or so on. So this is one of the best example where multimodal interaction is done. In the next slide, you can see the different parts of the camera in action. In the left top, you can see hand tracking, which is essential because the inspector is inspecting the part and moving his hands so that the particular interactive system has to be activated. And then there is a left bottom, face tracking is happening because the robot has to constantly see whether the inspector is looking onto the object or he is looking away. So on the right side, you can see the whole system in action, the projection. And this is one of the application areas where industrial inspection can be done with the AI vision technology. So next slide. So next is teaching robots. So we teach robots based on, like, there is a particular monitor. If you have seen industrial robots in action in pick and place, this pick and placing objects is the very most important basic function that a robot has to do. For this, the robot has to be manually programmed X, Y, Z coordinates, where it has to pick and then where it has to put the object. So we can teach the robot using the vision technologies. How we can completely take the digital version of this robot and put it into VR and try to follow the hand movements. So that is one of the high level task which we can do with AI vision system. So it is a very complex project which is still in ongoing one and interesting one. I'll move on to the next one. So the next use case that I'm going to talk about is also interesting one. We humans use a lot of keyboards, mouse, touch pads, and so on to interact with any kind of system. So what could be the next interesting stuff that we can do with vision technology? Next slide. So unfortunately, I couldn't play this video as well, but this is a video clip from Minority Report movie where Tom Cruise tries to, interact with a huge screen in front of him using his hand gestures. He will try to rotate his hands, try to have some kind of hand postures, through which he will manipulate the data. He will zoom in, zoom out, extract. He will swipe in, swipe out. All these are like gesture-based interaction with a huge monitor. How this is done is he will be wearing a blouse, which is having some motion sensors, which will send information back to the processing chip, and then it takes a decision to move up or down, zoom in or zoom out. Next session. And next slide, sir. So can you play the video here? Or not this one. Sir, not this video, actually 25th slide. I sent you by email, I think. Yeah, this one. So as you can see,
Orange Intelligenz.
so what you saw in that video is just a simple motion capture. Motion capture is the operator is wearing a gloves, which is consisting of all types of sensors connecting to the fingers, and the robot is exactly mimicking the motion of the operator. So the operator always has to wear this gloves and the small embedded chip, the processing chip on his body, in order to transfer the motion to the robot. So what could be even more better is natural way of interaction with a robot. You don't need any such mechanical gloves and sensors attached to your body, but you can have the sensors vision system installed in the surrounding, which can track your body motions, hand motions, and then transfer it to the robot in order to mimic the motion. Next slide, sir. In one of our project, we tried to do this based on 3D and 2D cameras. So next slide. So, but the problem was a lot of problems were there in order to like where the particular gesture is starting and where it is ending. All these were a problem, and operating environment should be more flexible to move your hands on. So there were a lot of challenges. Next slide. So that's where like we also again we need to include deep learning methods and machine learning methods where, for example, if you have to swipe right, swipe left, there are n number of motions that is occurring, like starting hand posture to ending hand posture, and then there is like transitional movement in between. So this is where you need to give a lot of input in order to get this particular recognition using the machine learning model. So this is one of the video. Again, I couldn't able to play it, but this video shows my colleague. He is trying to drive the industrial robot, which is on the other side, to just draw something on the touchpad, the interface. So he is using two hands to do some dynamic gestures so that the robot can follow that. And we have sensors installed on the bottom of the pad, you can see the sensors which are installed, which is like 3D sensors, and it can recognize your hand motion and transfer it to the robot. So this is one way much closer to the natural way of interacting with the robots instead of using mechanical gloves and stuff. Next. And yeah, we have arrived at the evolution, and this is one of my favorite use case experiment that I wanted to show: volumetric video production. So here also it involves n number of cameras. For example, this studio is in our institute here in Berlin, Germany. This studio captures volumetric video of any object, any human that walks into that room. It's a circular room. Rig consists of 32 high definition 8K cameras, which simultaneously takes images of you, and in real time it reconstructs your body structure. And then you can use this 3D in movies, gamings, VR, AR technology, and anything. So any immersive technologies you can use. So in our lab, in our institute, we use this mainly for film production. We have invited a lot of movie stars and sports stars in order to create 3D avatar of them. So can you play this video? This is a short one. So this is our studio in Berlin, Germany. Okay, so this is one of a kind studio, which is like first in Europe, using such a high technique cameras, and background processing involves a lot of computer vision algorithms, right from reconstructing your bags, your hair, your transparent clothing, your glasses, and everything is a very challenging task. It involves a lot of research. I remember there were like 4 PhDs out of that particular topic alone. And we have almost come to the end of the session. So I dissected some of the important aspects of how missions can see the physical world. And there are n number of other application areas which uses this. For example, inspection and quality assurance in production floor, mission vision, that is another topic. It's a vast topic. Healthcare devices, sports and entertainment, I showed the last video. In agriculture, they have vast number of applications: 3D metal printing, in-process quality assurance, smart mobility, and so on. So if you, next slide, sir. So these are some of the background knowledge that you have to have in order to get into this field. The very basic important things are a lot of mathematics, linear algebra, statistics, probability, 3D geometry in order to play with different sort of cameras. You need to know the knowledge of mathematics behind multiple view geometry. If you have to use different cameras, it involves calibration, precision to the millimeter levels, and so on. And next slide. So as a student, what you can do, you can play around and develop some nice applications. There are free databases available in the internet. There's a website called kaggle.com, which freely gives you a lot of data sets, image data sets, video data sets, hand, face, everything. If you just Google, you can download it. And these are the main vision tools that we use. Like OpenCV is vastly used in many of the industry projects as well. MATLAB is just like for prototyping. If you really want to know into this area, you can prototype some of the applications. It is very very intuitive and it's very easy to learn. And there are other tools as well in C Sharp if you are good in C Sharp. I use mostly OpenCV, C++, CUDA programming for fast and real-time applications. Next slide, sir. So, and for adapting machine learning and deep learning frameworks to take decisions about your vast input images, you can go for one of these machine learning, deep learning frameworks. TensorFlow is vastly used, and Keras is Python-based deep learning API. You can use Keras, Scikit, and TensorFlow. These are like vastly used, and there are n number of initial projects available in GitHub. You can download and play around it, utilize the time to understand how simple face recognition, hand recognition applications works. Next. Also, if you don't have a large, like nice computer which can, process your data, you can always go for some other API vision services like cloud-based services which are offered by Google, Microsoft, Amazon, but they are not free. You have to pay hourly based to use some for some calculations and stuff. But it's always good to explore it. Next slide. And if you want to learn about like right from the scratch how this particular thing works along with the mathematics and software background, you can always go for online courses. There are n number of courses available in Coursera, and you can select one of these courses which I listed in the slide and start utilizing your free time to read and get a certification. Next slide. Yeah, this is also like some of the courses. Recently, I saw Harvard is also giving some machine learning, artificial intelligence course, which is free, 7 weeks long. It's good to grab the opportunity right now. And I think we have come to the end of this session with this last slide. And I would like to say, if you want to recognize and see, play around your facial recognition softwares, there's a amazing website called Postnet where you can open the software in browser and the web camera automatically opens and tries to recognize your full body posture and so on. So you can play around it and see how your body poses are recognized. And as I mentioned, go to kaggle.com, download the data set, play around with Postnet, and you can, even if you have anything installed on your computer, you can go to Jupyter. It's a web-based a platform to run all these machine learning, deep learning, Python-based coding for developing simple AI vision systems. So I hope I gave some good general overview of how things work when it comes to vision system. So it's the end of the presentation.
Yeah. Rekha, the few questions. One is, it's possible can trained model can predict multiple objects without loss.
Multiple objects without
Loss.
loss. It depends on how much your model is capable of identifying, recognizing. It solely depends on how many nodes you use inside and how many layers you use. It depends on the whole construction of the process flow, right from the input. If you want to have a high, no loss of information from the input, you can go for deep learning models. As I mentioned, there are n number of optimized pre-trained models available for a lot of data sets. Also, you can use it for customized data sets, which is available in Model View webpage, which is also given in my PPT. You can try those models because based on the input, the loss can be different.
That's another question. What's the difference between HOG and YOLO object detection algorithm?
Those are like two different. YOLO is like you only look once. That means you just try to see the data set only once. You don't revisit it in a different time. It's like a one-shot based algorithm. And it's two different models which you use for two different sort of process flow. As I explained before, like different nodes, different layers, how much you want. It's a convolution based, or you want some feedback into the system. It's two different models.
I think that's it. No other questions. Okay, now it's time to conclude our event. Thank you very much, Rekha, for spending your valuable time with us. There are a lot of technical difficulty before we had. Anyway, we will successfully completed the presentation. I hope
Exactly.
everyone enjoyed the session. So thank you very much for the informative session, Rekha. On behalf of Jaya Group of Institutions and all participants, once again, thank you, Rekha. At
Thank
this
you.
juncture, I thank my management, all my colleagues who rendered their support for conducting this webinar series. And next schedule, it's on Monday. It's a weekend. Tomorrow and day after tomorrow, there is no schedule. And the next schedule on Monday at 6 p.m. So we have a speaker from UK is talking about how the payment processing can be done through online. So that's a talk on Mr. Satish Radhakrishnan is going to talk about the payment processing system. I request you all to connect at 6 p.m. on Monday. Thank you all for your great cooperation and kindly thank all the people who are responsible for the success for this event. Thank you one and all. Thank you. Thank you, Rekha.
Thank you.